Hey everyone, it's Justin again. Welcome back to our unit on piecewise functions. Get ready to piece it all together as we dive into graphing. By the end of today's lesson, you'll be able to graph piecewise functions. Make sure you have your PDF printed and ready to go. Also, have a pencil with an eraser. Let's get into it. Let's start by reviewing our definition. A piecewise function is a function defined by at least two equations, pieces, each of which applies to a different part of the domain. This piecewise function, f of x, consists of two pieces. The first piece is x squared if x is less than or equal to 1, and the second piece is 2x plus 2 if x is greater than 1. But what does that mean? Is x squared if x is less than or equal to 1. By itself, the equation of f of x equals x squared would have no restrictions on what x values could be substituted in. In other words, the domain is all real numbers. But when it's in a piecewise function, it has what's called a restricted domain. In this case, it's restricted to only numbers less than or equal to 1. So what does that look like on a graph? To start, let's graph the function f of x equals x squared and ignore the restriction on the domain for a moment. Pause the video and find example 1 in your PDF. Then fill in the table, graph the points, and connect them with a smooth line. Let's see how you did. This shape might look familiar, and you might remember that it's called a parabola. Notice that even though we only plotted 5 points, there are infinitely many points we could plot, which is why we continued the line past the plotted points and added arrows. Now, what we've graphed is the function x squared for all real numbers of x. But what we really want is just the piece that shows the function values when x is less than or equal to 1. What should we do? Well, we could just erase the part we don't need. If I want the part of the graph where x is less than 1, I should erase the part where x is greater than 1. X equaling 1 seems to be an important point. So what is happening when x equals 1? Because the interval is less than or equal to 1, 1 is included in the interval. Use a closed circle to indicate that on the graph. But what about all of the points where x is greater than 1? That's where the other half of our piecewise function comes in. Let's graph the function 2x plus 2 again, without the domain restriction. Pause now to fill in the rest of the table and graph the line. Don't forget your arrows. Great work. Just like before, we really only want part of this line, the part where x is greater than 1. Let's erase the part we don't need. Now let's think again. What is happening when x equals 1 in this portion of the graph? In this case, the interval is when x is strictly greater than 1. So we'll put an open circle here to indicate that we can use values all the way up to 1, but not including it. And now we're done. We've graphed the piecewise function f of x. We graphed a piece of a parabola when x is less than or equal to 1, and we graphed a piece of a straight line where x is greater than 1. The method we just used to graph this piecewise function, graphing each function completely and then erasing the part we don't need, is useful, but it's not the most efficient. Let's make some observations and then try another example. Notice for the first piece, x squared, that we only ended up using the points from the table of values that were less than or equal to 1. This was because the domain for this part of the function is x is less than or equal to 1. So with a little foresight, we could have made a table of values with only numbers less than or equal to 1, and then only plotted those points. We could have tackled the other part of the piecewise function in the same way, starting the table of values at 1 and then using values greater than 1. Using that method, let's try graphing another function. Now we have the function h of x, which has 3 pieces. For the first piece, we only want values strictly less than 0. Since 0 is not included in the domain of this piece, we'll know we need to use an open circle here. But we do need to know exactly where that open circle should go, so we need to include 0 on our table. When x is 0, this function would be equal to 1. So let's put that on our table, along with a reminder that we need to use an open circle when we actually graph that point. Then we can fill in our table with several more x values that are less than 0, so we can plot this function on the coordinate plane. Starting at x equals 0, we draw an open circle. Then we can continue with our other points, draw a line, and add an arrow at the end. No erasing needed. For the second piece, we'll only need values between 0 and 3. This time we have 2 points that are interesting. We should think about what's happening when x is 0 and when x is 3. Pause the video now, plot the points yourself. Because x can be greater than or equal to 0 for this piece, we should start at 0, 5 with a closed circle. Because x needs to be strictly less than 3, we'll plot an open circle at point 3, 2. Then we can plot the other points and draw the line. In this case, when we connect our plotted points, we ended up with a line segment instead of a ray. Now for our third piece, we want values greater than or equal to 3. Pause the video now to finish filling in the table and drawing the curve. Again, we start graphing at 3, 0 with a closed circle. Continue plotting. Draw our curve with an arrow at the end. Notice that this part might start off looking like a straight line, but it is a quadratic, so it will have the curve of a parabola. Great work. Now it's your turn to try. Before we begin our final example, here are some reminders. Start and sometimes end your table at the value given in the domain, regardless of the type of inequality sign. Use 3 points in the table to ensure the graph has the right shape. Use a closed circle for or equal to inequalities, otherwise use an open circle, and add an arrow if needed. Pause the video now, fill in the tables, and graph the piecewise function. Welcome back. Let's see how you did. The first piece, g of x equals 4, is what's called a constant function because no matter what the x value is, it always outputs a value of 4. When we graph constant functions, we always get a horizontal line, and in this case, we're starting at x equals 0 and only graphing the x values less than that. Don't forget your open circle and an arrow. The second piece, g of x equals negative 2x plus 4, will only need the values from x equals 0 to x equals 1. We could include some more values in between, but it only takes 2 points to make a line, so we can just use those two. This time, we have a closed circle at x equals 0 and an open circle at x equals 1. Now, something interesting has happened here, and you might be wondering how to deal with it. In this function, And in many other piecewise functions, there's an overlap. In the first piece, we start at the coordinate point 0, 4 with an open circle. And in the second piece, we also start at the coordinate point 0, 4, but with a closed circle. There's a lot going on at that point. So what does it mean to have an open and closed circle on the same point? Does the function have a point at 0, 4 or not? Well, which piece of this function tells us what happens when x is 0? The domain of the first piece is all values of x that are less than 0, but the second piece tells us what happens when x is equal to 0. And when x equals 0, g of x does exist, and it's equal to 4. So the closed circle takes priority here because the function as a whole does equal 4 when x is 0. We don't need an open circle and a closed circle on the same point, so we can just erase the open circle from the first piece, and the point 0, 4 will just have the one closed circle on it. All right, the third piece, g of x equals 3 times the quantity x minus 1 squared minus 3, should only use values of x that are greater than or equal to 1. So we can start our table at x equals 1 and add a few more values that are greater than 1. Then we can graph using a closed circle and an arrow. Notice that this part might start off looking like a straight line, but it is a quadratic, so it will have the curve of a parabola. Great job! In today's lesson, you learned how to graph piecewise functions. Be sure to complete the activities in your PDF as well as the online practice. Next time, we're going to learn how to evaluate piecewise functions. See you then!
Hey, hey.